Good morning, dear students. Continuing with the last lecture on electrolytes concentration cell with transference. Today we will discuss on the topic liquid junction potential. Now what do we mean by liquid junction potential? It is the potential which is set up at the junction of two solutions due to difference in the speed of ions moving across the boundary. We very well know in case of electrolyte concentration cells with transference, the two electrolyte solutions are in direct contact with each other through a permeable boundary. Now across this boundary there is movement of ions in both the directions. Now due to difference in the speed of ions, a potential is set up at the junction of two solutions, which is known as liquid junction potential. Now when the cell acquires liquid junction potential represented by symbol EJ, the EMF of cell is not equal to the sum of electrode potential due to the cell reaction taking place. It will also include the liquid junction potential set up because of difference in the speed of ions across the boundary. So in this case, total EMF of the cell will be equal to the sum of electrode potentials plus liquid junction potential represented by the symbol EJ. Now we have already gone through this concentration cell. In case of this concentration cell, the overall electrode reaction taking place is H plus ions are moving from the solution of activity A2 to the solution of activity A1. Now, sum of the electrode potential for this concentration cell was found to be RT by F log natural A2 by A1. Now, presenting these activities in terms of molality and activity coefficient, we can write E1 plus E2 will be equal to RT by F log natural M2 gamma 2 divided by M1 gamma 1. Now, we have already calculated in our last lecture, in case of concentration cell with transference, total EMF of the cell was found to be 2T negative RT by F log natural M2 gamma 2 divided by M1 gamma 1, where we have included all the electrode potentials due to the cell reaction as well as the potential set up due to the liquid junction potential. So EJ, which is the liquid junction potential, will be equal to the total EMF of the cell minus EMF of the cell due to only electrode potentials occurring due to electrode reactions. So we are having EJ is equal to 2T negative RT by F log natural M2 gamma 2 divided by M1 gamma 1 minus RT by F log natural M2 gamma 2 divided by M1 gamma 1. Now we very well know T negative plus T positive, that is equal to 1 always. So we can write here T negative minus 1 is equal to minus T positive. So we are having liquid junction potential is equal to T negative minus T positive into RT by F log natural M2 gamma 2 divided by M1 gamma 1. This is the resultant expression for the liquid junction potential. Now next one is, what are the various applications of concentration cells? So the first one is determination of activities and activity coefficients. We have already gone through this, that we can replace the activity by product of molality and activity coefficients. Now considering the example of this cell in which hydrogen at 1 atmosphere is in contact with the HCl of activity A and which is further in contact with the silver chloride electrode. Now this is the cell reaction for this type of cell. In this case we are determining the activity coefficient of HCl. Now, according to Nernst equation, the EMF of the cell is given as E naught silver chloride minus RT by F log natural activity of H plus activity of chloride. As you can see the last reaction, when you are applying the Nernst equation to this one, we will get EMF of electrode potential or EMF of the cell is equal to standard EMF minus RT by F log natural activity of H plus ion into activity of chloride ion. Now the product of these two ions, we can write the activity of the electrolyte. Now replacing this negative sign by positive sign, we are having here log natural 1 by A, and putting activity is equal to the product of molality square into gamma plus minus square. We will have EMF of cell is equal to standard EMF minus 2 RT by F log natural molality minus 2 RT by F log natural gamma plus minus, where gamma plus minus is the mean activity coefficient of hydrogen ion and chloride ions present in the solution. Here we have put activity is equal to m square gamma plus minus square. Now next application is the determination of standard free energy change and equilibrium constant. We very well know in a cell the electrical energy produced is always equal to the decrease in free energy accompanying cell reaction. Mathematically we can write minus del G is always equal to NFE, where E is the EMF of the cell. And if we talk about the standard state, we can write here minus del G naught will be equal to NFE naught. Now, equilibrium constant is related to the standard state free energy change by this relation, where minus del G naught is equal to RT log natural K. So by knowing the standard EMF of the cell, we can find out the standard free energy change, and from standard free energy change, we can easily calculate the equilibrium constant. Now next one is the determination of valency of the ions. The EMF of a concentration cell is given by this general formula. We have already studied this, where N is equal to the valency of the ion. So if we know the EMF and various other terms, we can easily find out N, which is known as the valency of the ions. Next one is the determination of solubility product. Now EMF of a concentration cell is given by this general formula. We very well know activity can be replaced by the concentrations here. Now knowing the EMF of the cell and concentration of ions in one of the solution, we can easily find out the concentration in the other solution. If we very well know the EMF of the cell and concentration of ions in one of the solution, we can easily find out the concentration of ion in the other solution. Now, if the second solution is that of the sparingly soluble salt, we can write here C2 is equal to the solubility of that solution. If the second solution is that of the sparingly soluble salt, its concentration would be nearly equal to its solubility. So in this way we can find out the solubility of that solution. For example, we are taking here this cell. In this case, silver is in contact with the silver chloride and dissolved in it is in contact with the solution of KCl of normality 1 by 10. And here the silver electrode is in contact with the solution of silver nitrate of normality 0.01 normal. Now the EMF of this cell is given by this expression, where C is the concentration of Ag plus ion in the KCl solution. Now as silver chloride is sparingly soluble in this KCl, so the chloride ions are produced mainly from the KCl. The reason being, chloride ion produced from the silver chloride will be negligible as compared to produced from the KCl solution. So we will write here the concentration of chloride ion is approximately equal to the concentration of KCl, which is equal to 0.1 molar. Now the solubility product is given by the product of concentration of Ag plus and Cl minus, and the concentration of Ag plus is given by C, which can be calculated from the EMF of the cell, and concentration of chloride ion is equal to 0.1 molar. So we can easily find out the value of solubility product of silver chloride. Now next and very important application of concentration cell is the determination of pH of a solution. The pH can be defined as minus logarithm of H plus ion concentration. Now what is the basic principle to determine pH using EMF measurement? How we do this? We set up a cell in which one of the electrode is such whose electrode potential is depending upon the concentration of hydrogen ion, whereas other electrode taken is a reference electron, which we generally taken as calomel electrode. Generally, the electrodes used for determination of hydrogen ion concentration whose electrode potential depending upon hydrogen ion concentration are hydrogen electrode and quinhydron electrode. So first one is the determination of pH of a solution using hydrogen electrode. In case of hydrogen electrode, the half cell reaction can be written as H++ electron giving 1/2 hydrogen. Now electrode potential for this half cell can be given as equal to E naught plus RT by F log natural concentration of hydrogen ion, and the standard electrode potential of hydrogen electrode is taken as 0. So we will have electrode potential is equal to RT by F log natural H plus. And at temperature 25 degrees Celsius, putting the value of R and F, we will get the electrode potential for this half cell is equal to 0.0591 logarithm of hydrogen ion concentration. Now, how we determine the hydrogen ion concentration or pH of the solution? We combine this hydrogen electrode with the reference electrode known as calomel electrode. Now what happens? Oxidation takes place at hydrogen and reduction takes place at calomel electrode. So by convention we can represent the cell by this presentation, where platinum hydrogen 1 atmosphere is in contact with the hydrogen ion of unknown concentration, and it is further connected to the reference calomel electrode. Now EMF of the cell will be given by the electrode potential of right hand side minus electrode potential of left hand side electrode, and the value of this electrode potential of this calomel electrode is given as 0.2415 minus 0.0591 pH, which is the electrode potential of this hydrogen electrode. So we can easily find out the pH of the solution if we know the EMF of this cell. So this is the method of determining the pH using hydrogen electrode. Next one is the determination of pH of a solution using quinhydron electrode. Now what do we mean by quinhydron? It is an equimolar mixture of quinone and hydroquinone that is known as the quinhydron. Now this quinhydron, which is a mixture of quinone and hydroquinone in the presence of hydrogen ion, gives a reversible redox reaction. Quinone plus 2H plus 2 electron, they are reversible with hydroquinone. Now the electrode potential of half cell is given by the Nernst equation. EQ is equal to EQ naught plus 2.303 RT by NF log. As we are taking here the reduction reaction, here we will put minus and then we will write QH2 divided by Q into H plus square. So taking in reverse, we will write here EQ is equal to EQ naught plus 2.303 RT by NF log Q into H plus square divided by QH2. Now as the quinhydron is containing the equal amounts of Q and QH2, so we can write this by this is equal to 1. Concentration of Q divided by concentration of QH2, that is equal to 1. So putting this value, we are getting the resultant expression for the EMF of the cell. Now EMF of the cell is equal to electrode potential of this half cell is equal to the standard electrode potential plus 2.303 RT by F log H plus. Here we are putting the value of N equal to 2. As we are seeing in this reaction, there is 2 electrons are involved. So we can put here N equal to 2 to get the resultant expression for the electrode potential of quinhydron electrode. At 25 degrees Celsius, putting the various values, we will get the resultant expression EQ is equal to EQ naught plus 0.0591 logarithm of hydrogen ion concentration. Now the value of standard electrode potential of quinhydron electrode is given as 0.6996 volt. Now to determine the pH of the solution or to determine the concentration of hydrogen ion in the solution, we connect this quinhydron electrode to the standard reference calomel electrode. So the cell can be represented as like this. Now in this case, what is happening at quinon, there is reduction is taking place. At calomel, there is oxidation is taking place. So EMF of the cell will be equal to E of right minus E of left. So we can write here EQ minus E calomel. Substituting all the values, we are finally getting the pH of the cell is equal to 0.4581 minus EMF of the cell divided by 0.0591. So knowing the EMF of the cell, we can easily determine the pH of the unknown solution. Now what are the various merits of this quinhydron electrode? It is easily set up by immersing a platinum strip in the test solution and by adding just a pinch of quinhydron. Whereas in case of hydrogen electrode, we had to supply hydrogen gas continuously at a particular pressure. Now second thing, which is the demerit of the quinhydron electrode, is that it doesn't give accurate results for the solution having pH more than 8.5. Or you can say it is not giving the accurate results for the alkaline solutions. The reason being due to the oxidation of hydroquinone in alkaline solutions. So in the next lecture, we will continue with the potentiometric titrations.